Most applications of large language models and AI systems nowadays involve retrieval augmented generation. And retrieval augmented generation is basically the act of taking other documents, other information that might be in your business, might be on the internet, wherever, taking that information, chunking it up, and comparing it with a user's query, grabbing the information which is most relevant for that user's query, and sticking it into the context window of the large language model so that it can reason over that new data, that external data. And one piece of that I've had people asking me questions about is, how does that comparison happen? And you've heard the word, or you may have heard the words cosine similarity, and which is kind of the primary method for doing this. It's one of several you could have, but I'd say that's the primary method. And as a physicist, or we actually use this a lot. And so I thought it would be interesting to just go through the basic mathematics of what that is, what that means, and see if it's useful for you. So here's the basic idea. Large language models are going to take in text, so a string of tokens, and they're going to give a string of tokens back. The query, the user's query, will be a string of tokens, so some text. That text is going to get turned into an embedding vector. So this is like a one-dimensional kind of matrix. It's just there's a number here, there's a number here, there's a number here, dot, dot, dot. And it's depending on what you're using for the embedding. It could be 1,500 numbers long. And there you want to be able to cram, in addition to your query, into this context window, some pieces of documents which might be relevant for this query. So how do you know what pieces of these documents are relevant? Well, these pieces of documents are turned into or chunked up into little pieces of text, which they themselves get turned into a long list of numbers or an embedding vector, dot, dot, dot. And so I keep using this term vector. I'm a physicist or astrophysicist by training. So we use vectors all the time. Vectors are just things that have a magnitude and a direction. And typically we represent that by so this here is my vector. So we denote these by arrows a lot of times in physics. And there's going to be some coordinate system. So in a really simple two-dimensional case, this could be, the y-axis, like the vertical axis, and the x-axis or something like that. So this is a simple two-dimensional vector. And, if I were to represent this two-dimensional vector as a list of numbers, what I would do is I would just figure out what the x, how far along in the x-axis it is, and then similarly, how far along the y-axis it is. And I would put the number for in the x direction here and the number for the y direction. So it's just going to be, for this little two-dimensional one, it's going to have two numbers in it, which represent the sort of where it is along the x, assuming you put the end of that arrow at the origin, at the beginning of x and y, and the second number would correspond to y. Now, in the case of these embedding vectors, they're massive. They're multi-dimensional, 1,000 or more, around 1,500, let's say, of these numbers. So this could be these 1,500 dimensions, right? So I can't draw a 1,500 dimensional vector or arrow. I can draw a two-dimensional one. If I'm clever, I can draw a three-dimensional one. I can't draw a multi-dimensional one, but it has the same idea in terms of the same sort of properties, right? So what is this similarity, cosine similarity that we're talking about? How do I tell whether this embedding is close to this one? So in the way we do it is there's something called the dot product or the inner product of two vectors. So let's say I have two vectors, one's over here and one's over here. What I do is I put them at their origin. I represent them as these arrows. And the dot product or the inner product of let's call this vector A. I'm going to put a little arrow over it just because I'm a physicist and I can't help myself. That's not how probably a data scientist would do it, but who cares? So an inner product or the dot product of these two vectors would be represented by this little symbol here. Now, what is it? So basically, what you do is you take the first element of A, well, I'll call that, let's say, A1, and the first element of B, so, well, B's over here, B1, and I'm going to multiply them by each other. And then I'm going to add I'm going to take the second element of A and the second element of B, and I'm going to multiply those by each other. Now, if this was just these two-dimensional vectors, I would stop there because there are only two numbers. And this is a single number. Even though vectors are things that have magnitude, like a length, and a direction, they're represented by multiple numbers. When I do this inner product, I just get a single number back, which is given by this. Now, it also happens, if you do the math, this is also equal to the magnitude of A, meaning the length of A. How long is this? Times the magnitude of B times the cosine of the angle between them. I'll represent the angle as theta. This is something that would be like in degrees or radians, whatever angle you want. And so this is also true, that it's equal to the magnitude. So what's the magnitude here? Magnitude of A would just be given by using Pythagorean's theorem, where A squared is equal to A1 squared plus A2 squared. This is just Pythagorean's theorem, because I can make a little triangle here out of A. And one side of that triangle is the X, or A1. The other side of the triangle is the Y, or I'm calling it A2. And then that means the hypotenuse, which is the length, is just this. So in order to get the magnitude of A, I just take the square root here, like that. And similarly, the magnitude of B is just square root of B1 squared plus B squared. So how do we use this? If these embeddings represent the meaning of these sentences or these pieces of text, which they should, and I can talk about that in a different video, how they do this encoding, then the closeness of them, how close they are to each other, should represent how close they are in meaning as well. And so what you do is you use this inner product, so to solve for the cosine of the angle between them. So that is simply going to be 1 B1 plus A2 B2 divided by the magnitude of A and the magnitude of B. I've just solved, I put this equal to that, and then I divide it by A and B. Now, in the case of these embeddings, what would happen is I'd have plus ... On the top, I'd have a lot more terms. And if it was one of the 1,500 or so vectors, I would have 1,500 terms along here. And this measurement, so the closer they are together, so when the angle goes to 0, meaning they're right on top of each other, then the cosine of that angle goes to 1. And if they are pointing in totally different directions, in physics we call that orthogonal, then the angle is 90 degrees, then it goes to 0. And if it pointing like in the totally other direction, it would actually get a -1, meaning they're opposites of each other. So this is the basic math behind the cosine similarity. And all that RAG is doing is saying, here's my text, my prompt, I make it a vector, I chunk up all my documents, I make them a bunch of vectors, and then I go calculate for each one of them, for each pair, or I take the prompt and I take that piece of text, I am going to get a cosine similarity, and then I choose some threshold. I take the top 5, or I take the above a certain cutoff to make sure that I'm only putting things that are really similar and relevant into the context.